In this video, we'll be looking at how to create a container emitter and how to render foam in Arnold. If you want to follow along, download the zip file in the description section of this video and extract it anywhere in your file system. To start, open the boat.max scene. In this scene, we applied a path constraint to the following helper object to steer the boat in front of the camera. Once the boat leaves the frame, we kept a chunk of time to watch the foam settle on top of the liquid. To render the result, we'll be using Arnold in its default settings. In terms of lighting, we've kept it simple by assigning an Arnold physical sky to the scene's environment map. Instead of setting the sky's intensity to 4 like we did in part 1, we've chosen to install an exposure control on the physical camera, which we've kept to the default value of 6. When we do a test render of the animation, say on frame 28, we should see the speedboat floating on a black background. Which brings us to the main point of this tutorial. Let's add some foamy water under the boat. We'll start by creating a box centered at the origin to fill the camera's frame. Since that box will be acting as the emission container for the liquid, we'll name it Water Container. To eventually see the liquid, we'll need to make the box transparent. To do that, go to its object properties, set the visibility to 0.1, disable the renderable attribute, and enable see-through. Now if that's all we did, the liquid would start falling the moment it's emitted inside the container. To keep all that liquid in place, we'll need to add some kind of invisible bathtub. We'll create this bathtub by starting with a cloned reference of the water container. Set its name to Water Boundary. Enter isolation mode. Then add an Edit Mesh modifier. Select the top face and press the Delete key to create a hole. Add a shell modifier to give it some thickness. When you're done, exit isolation mode. We'll use Edged Faces mode to get a clear picture of our setup. Now in case you were wondering about our choice to clone as a reference, we did that to keep our options open. If we ever want to resize our container, we can simply change its height and the boundary will adapt accordingly. So now we're ready to create our water. Under the Create tab, select Fluids, Max Liquid. Click and drag in the viewport to create the liquid icon. Place it above the working area. Name it Liquid Ocean. Then, to start working on its parameters, open the simulation view. Under the Liquid Attributes tab, make sure the icon type is set to Custom. Then, add the water container as an emitter. To make sure the liquid doesn't keep falling, add the water boundary to the collider list. We also want the boat to create a wake along the surface, so we need to add it as well. While we're at it, we should create a kill plane to avoid simulating any particles that splash out from the boundary. The kill plane can be any size. The thing to keep in mind is that particles that cross the infinite span of the plane will be removed from the simulation. Just like in part 1, we'll disable the renderable attribute and enable display as box so it doesn't get in the way. Move the kill plane below the water container to avoid killing particles on the liquid surface. Once it's in place, add it to your liquid attributes. Now that we've added all our actors, it's time to configure the solver. Select the water container inside the solver parameters. We've only got one emitter in our simulation, so it comes down to a personal preference whether to edit the global emitter settings or to modify an individual emitter. For this scene, we'll choose to work on the water container individually, so enable its override checkbox. To make sure it only gets filled once, we'll set its type to container. If we kept it in emitter mode, more liquid would be created to fill the gaps as the boat passes through. Now let's hop over and configure the colliders. The global collision settings work well for the water boundary. However, when it comes to the boat, we'll need to override those settings. If we look closely, the boat contains a lot of curved surfaces and has several openings that lead into its main cavity. Because of its geometry, we recommend the solid robust conversion mode, which is also useful for meshes that contain open edges. Actually, one hint that you might need the solid robust mode is if you start seeing large unexpected splashes in your simulations. Now the last detail we need to address before we can hit the Solve button is to increase the master voxel size. Based on the current size of our objects, our computer might run out of memory if we run the solver with a master voxel size of 0.5. Instead, we'll set it to 10 for our first test run. Given our ocean setting, we want to create some foam as well, so make sure to activate the foam solver. Then, when you're ready, press Solve. We've got something, but it looks like our boat is cruising through a thick, blocky soup. Let's go modify some display settings. To avoid the blocky preview, set the liquid's display type to plain, and do the same thing for the foam. The viewport might feel slower at this point, but we can get back to a working frame rate by reducing the number of displayed particles. At this point, we see our liquid and our foam, so let's get to rendering. We'll first need to assign a material to our liquid. In fact, since we're dealing with foam, we'll need to work with a multi-sub-object material. The first slot is for the liquid, while the second slot is for the foam. We'll assign a physical material for our liquid. To make water, set the base color to 0, the roughness to 0.1, the IOR to 1.33, the transparency to 1, the transparency color to a light blue, and the transparency depth to 100 to give clear droplets. Now, when it comes to rendering foam, the one thing to keep in mind is that it's more of an art than a science. In this video, we'll make use of the default foam rendering options. In the next video, we'll take the time to explore different foam rendering techniques. For now, the basic method is to use a white physical material. Make sure the foam's render settings are set to Arnold point. Then, hit Render. If we look carefully, we see a few little points inside the water. Of course, it would be a pretty big stretch to call that foam, and the result we have here is drastically different from what we have in the viewport. So what gives? In this case, our current display settings are actually leading us on. To get a closer match between what we see in the viewport and the rendered result, change the foam's size channel to density. Over in the render settings, we're using a radius of 0.2, meaning that the highest density particles are being assigned to a radius of 0.2. To get a better preview from our display settings, decrease size max to a matching value of 0.2. For an even better comparison, try increasing the displayed liquid amount. The rendered foam effect is a bit underwhelming in this configuration, so let's increase the density radius to 1. When we render again, the foam really stands out, but the point size gives it a slightly grainy appearance. To fix that graininess, we need to increase the simulation resolution. As usual, we'll start by cloning our solver to track our progress. We'll name this one Solver High Res. Set the master voxel size to 4, then go ahead and press Solve. When we render our new result, we see a lot more detail at this resolution, and the foam particles give a better impression of splashing droplets. To get a sense of how the animation flows without rendering the whole thing, we can grab a preview of the viewport. Make sure to activate the camera's viewport, then create the preview under the Tools menu. This preview looks good, but let's say we wanted the foam to last longer on the surface. For that, we'll need to modify the foam parameters. Foam gets emitted when all the minimum parameters are fulfilled in a region of the liquid. The minimum speed is self-explanatory, but the difference between churn and curvature isn't so obvious. Churn refers to the amount of rotation happening inside the liquid, whereas curvature refers to the surface of the liquid. The amount of foam we're generating is good for the simulation, we just want it to last longer. For that, we'll need to go into advanced mode. We get a whole collection of new parameters, but the one we're interested in is the dissipation rate. Lower values give the foam a longer lifetime outside the liquid, so we'll decrease it to 2. Let's run the solver again to see what we get. Now that the solver's done, we'll create a new preview to compare our results. Because of the dissipation rate, our foam is now lasting much longer. The last step before we hit render is to build our mesh cache. Now that that's done, we can render our main sequence. It looks like we've got a good starting point for our foam, and in the next part, we'll build on this scene to explore different foam rendering techniques. I hope you found this helpful, and thanks for watching.